Lesson 209, we're introducing vectors today. Vectors are things you can use to represent like forces, velocities, and other kinds of things. Think about a velocity. If you've got a velocity, you've got two numbers going on. You've got how fast are you going and which way. So there's two numbers to it. So we tend to represent velocities, forces, and other things as arrows. So vectors are like arrows. So you can see we got some arrows in front of us down here. Now, it turns out there's various ways you could represent these arrows or describe these arrows. You could draw them, of course, which is what we've done here. But look at this thing. By the way, that symbol means pounds. So this is a 50-pound force pushing that way. There's three ways, at least three ways, that we could describe it. One way you could describe it is you could say, well, it's 50 pounds pushing to the east. Something like that. It's supposed to be more natural to say to the east if it were a velocity, 50 miles an hour to the east, but you could do the same thing with pounds. He's pushing 50 pounds to the east, something like that. That would be a nice verbal description. Another thing you could do, and you might like this kind of description, it's my favorite anyway, is to say you're pushing 50 pounds. And remember this idea of angles in standard position, where here's the x-axis and you basically start at the x-axis and you rotate counterclockwise, and these are called standard position angles. So you could say, well, what's that standard position? That would have to be 0 degrees. So you'd say I got 50 pounds pushing at 0 degrees, standard position. That's a great way to represent these things. This actually has a name. It's called polar form. And I think it's polar form because you kind of think of this as a big old pole here at the origin. And it's kind of like telling somebody, which way do I shoot the spud gun? That way. And how far do you want me to shoot it? You know, whatever. So those are the two numbers. So anyway, polar form is when you give the magnitude. We often call this the magnitude. How strong is the force? And the direction, which you can stipulate the direction in different ways. You can say, you can draw the arrow, say that way. You can say to the east. You can say standard position 0 degrees. Here's another form that you can use. What you do is you kind of think in terms of X and Y coordinates, kind of, sort of. So look at the end of look at where it's pointing to. It's pointing over to there, right? So to get from here to there, you would move basically 50 along the x-axis, and you wouldn't go anywhere along the y-axis. So you could say it's 50 pounds along the x-axis, and there's no pounds along the y-axis. And this is called rectangular form because you're giving rectangular coordinates, kind of, sort of. You know, so far along the x-axis, so far along the y-axis. These two forms are going to be mathematically the ones that we use the most. We will go back and forth between them, actually. So a lot of times we'll use polar form. It's nice and descriptive. You got to dig it. A lot of times we'll use rectangular form. There's also advantages to rectangular form as well. And often we'll describe our vectors like this, you know, to say, well, this is what's going on here. And then we translate the verbiage into the math forms, this or this, and we do our math. So anyway, that's common. Today's lecture, I just want to focus on representing the vectors. Just representing the vectors. Let's go down to this one. How would you represent this vector? Well, you could draw it like we did. How could you describe that with words? You could say it's 40 pounds, and you could say it's, well, it looks like it's going due northeast, doesn't it? So you could say pushing due northeast, because it's exactly in between north and east, due northeast. What would polar form look like? You'd give the magnitude, how strong is the force, 40 pounds, and then you'd say, which way is it? And again, you would use standard position. So you would rotate from the x-axis and you'd say, well, it's at 45 degrees. There's our polar form. That's pretty cool. Now, to get the rectangular form, you have to think about basically shadows on the x and y axis, kind of like. You have to say, well, to get to this point, how far would I have to go along the x-axis? How far would I have to go You could say along the y-axis, or you could say in the y direction, however you want to say it. And if you trust me, I did a little SOHCAHTOA ahead of time, and hopefully you'll trust me on this. You can try it yourself, make sure you get the same thing. But it turns out this is about 28.28 pounds along the x-axis here, and then this would be another 28.28 pounds. And again, you can say along the y-axis, or you can say in the y direction, however you want to say it. So here's our two forms, two main mathematical forms for that vector. 40 pounds at an angle of 45 degrees, polar form, wonderful. 28.28 along the x direction, 28.28 along the y direction. Rectangular form, also wonderful. Let's come back up to the top of the page. How would you describe this one? Looks like I better get some border lines in here. How would you describe that force? Well, let me give you a hint. That's supposed to be a 30-degree angle right there. That might help, right? Now, actually, I don't know that you would... I don't know how many of you know this already, but there's a way of describing this bearing, so to speak. We use it like with boats and stuff. We would say we've got a 60-pound force with a bearing. I guess bearing really makes more sense for velocities, but whatever, we'll use it here. With a bearing of, and here's how you state the bearing. You start by first either saying north or south. Now, it makes sense that we're going to say north first, because we rotate from the north to get over here. And actually, we would rotate from the north this far. Bearing of north 60 degrees towards the west. Okay, so dig how this works. Face the north, turn 60 degrees towards, I'm trying to fit the word towards in there. Face north, turn 60 degrees towards the west. That's how you read those things. Bearing of north 60 degrees west. So we'll see that bearing kind of notation come up. So let's explain it here. Maybe I should leave that here as like worthwhile notes. So you face north, you turn 60 degrees towards the west. And that's one way you could describe this vector. You want to use polar form? I sure do. I like polar form. It's basically my favorite. Tells me which way to shoot the spud gun and how far. 60 pounds! And what would be my direction? Now here's the thing. We're supposed to use standard position. Use standard position. So again, that's rotating from the x-axis over to here. So if that's a 30, this would be 180 minus 30. This would be 150 degrees. And so let's make a note to ourselves here. When you're using polar form, you're basically supposed to use standard position. And again, that's rotating from the x-axis. That's a positive rotation if you go counterclockwise. You could give a negative angle. Like you could take an angle like this and say, oh, that's negative 45 degrees. That still counts as standard position because you are going from the x-axis. But anyway, go from the positive x-axis when you're using this polar notation here. What about rectangular? Well, again, if you trust me, I did some XY components here. I did a little trig action. Let's say I did my trig in green. So you have to kind of, I'm thinking in terms of dropping a plumb bob, like we did, wasn't that the last lecture, dropping a bunch of plumb bobs, or anyway, a recent lecture. And you figure out, well, how far, to get to this point, how far would I have to go along the x? How far would I have to go along the y? And it turns out along the x, you would have to go a distance of 51.96, and along the y, you would have to go a distance of 30. Now, what is the x and y that I put in my little brackets here? Well, you got to take into account that 51.96 is in the negative x direction. The y 30 is in the positive direction. That's okay. But yeah, you want to say it that way. So I should be making some circles here, shouldn't I? That was the answer to that one, and here's the answer to this one. By the way, just as a side note here, sometimes this is called the x component of the vector, and this is called the y component of the vector. Component basically means piece. So it's kind of like this 60-pound orange vector here has two parts to it. You go along the x-axis this much, so we call that the x component. You go along the y direction this much, so we call that the y component. So it's, I think it's a natural choice of words anyway. Okay, one more to play with here. We might describe this, well, if we want, we can use that bearing lingo. 70 pounds with a bearing of, now this time, remember with bearing, you always start with north or south. You never start with east or west, by the way. You always start with north or south. I believe this might be the same with civils. I should ask a civil guy one of these days, civil engineer tech guy. Anyway, so we're down here, so we'll start with south, and then you would rotate how far? Well, I meant for that to be a 30 degree actually, so let's just trust that. South and then 30 degrees towards the east. Remember, you face the south and then you turn 30 degrees towards the east. That's what the bearing notation is all about. Face south, turn 30 towards the east. Cool. So that'd be one way to say it. You could say this as in polar form. You would say 70 pounds and the direction would be, and you'd want to use your polar notation. So if this is a 30 here, polar, you use standard position, which means from the x-axis. That would be a negative 60 degrees. And you could call it negative 60 degrees. That's okay. It's from the x-axis, the positive x-axis. That's what matters here. You could just as easily, if you wanted to, you could say 70 with an angle of positive 300 degrees. That would also be correct. As far as x components go and y components go, I trigged it out. So if you trust me on this, you can get some more SOHCAHTOA practice if you want to check my answer. But it turns out that the shadow this way was 35, and the shadow going this way was 60.62. Or you could say how far along the x-axis 35, how far along the y direction 60.62. You don't have to draw all this stuff. But that means that we would say along the x direction 35, along the y direction. Now notice we're going down, so you got to pay attention to which way, right? Pay attention to which way when you're doing this stuff. If you're going up, you'd say positive. If you're going down, you'd say negative. If you're going to the right, you'd say positive. If you're going to the left, you'd say negative. Just like the usual sense of direction on XY axes. Positive up, positive right, negative left, negative down. Okay, so I wanted to kind of give you several examples of what the polar form might look like, of what the rectangular form might look like. Again, make sure your theta is in standard position. That's important when you're doing polar form. And also make sure you take into account positives and negatives when you're doing your rectangular stuff, your rectangular form. Okay, next page I got two examples where we're basically going to practice. We're going to say, okay, somebody gave us a vector in rectangular form, or at least they gave us the x and y components, and then we're going to turn it into polar form. So two-step process really, and they don't always say step A, but it's a very good idea to always do this first. Draw the thing so you get a handle on what's going on. So Biff's vector has these two components. So let me draw like an XY axis real quick. So along the x direction, go 12. Go 12, young man. That's positive 12. I'm going to label that as a 12. And then along the y direction, go negative 8. So you can either draw it over here or you can draw it over here. It doesn't matter where. So maybe I'll draw it over here, or I'll label it over there anyway. That's a negative 8, but of course that's a negative 8 as well. Where do you end up? Now, we're drawing all vectors from the origin, which means draw this from the origin too, okay? And if you want, you can complete a little rectangle like this. So this side has a side of 12, you know. It's a nice rectangle, but maybe I should emphasize this is the vector we're talking about. You can kind of check by going like this. X is positive, y is negative. Well, that means if x is positive, you go right, and if y is negative, you go down. So we're going right and down. Right and down. This one goes right and down, not this one. Right? Not this one, this one, this one. This one goes right and down. So that's how you can check that you're kind of drawing the right vector here. Now we want to express that in polar form. So what I'm going to do is I'm going to lift out a triangle just so I can focus on myself here. I don't like it when my diagrams get too busy. So I'm just going to pull out that triangle there. We'd like to know how big this side is. Well, we can do Pythag, right? So you do the old 8 squared plus 12 squared, because this is a right triangle. And then you would have to take the square root. And when you do that, I did that. What'd I get? I got a 14.42. Cool beans. That's how long this is. This vector has a length of 14.42. What's the direction? Well, I should kind of solve for this theta here, right? And I could do a, let's switch colors. I could do one of those TOA, tangent type things. So the tangent of that angle is 8 over 12. And if you do a shift tangent, that's giving us a theta of 33.7 degrees. Okay, I think we're ready to write our answer now. So we got the basic information. How long is the vector? The vector has a length of 14.42. Which way does the vector point? Again, you want to use standard position. This angle is 33, right? This angle is 33. What's this angle? Well, it's the same as this angle, really, except in standard position, you would want to say negative 33.7 degrees. Again, always with the standard position for polar form. Okay, so keep that in mind. You can do the SOHCAHTOA and the shift tangent and all that stuff and solve for your numbers, but just make sure that when you're putting it into the final form, you're taking into account, okay, I'm supposed to use standard position, and really that's a negative rotation from the x-axis. So, okay, let's look at this one. Bonnie's vector has, okay, I like to do this. Vx is negative, Vy is positive. X is this. So that means left and up, right? You go negative x direction, that's left. You go positive y direction, that's up. You're going left and up. Okay, let's draw the vector then. We expect it to go left and up. Left by how much? 14. So I guess I could call this negative 14 because that's what it says. Up by how much? Up by 20. And I think I'll draw it over here. It seems to... Technically, you could draw it over here, but I don't want to draw too many things. So I'm going to draw it over there. There, boom. Now this is the R, and we could start solving for R by saying, well, Pythag, right? So you could say negative 14 squared plus 20 squared. You don't have to use a negative 14 because you're going to square it anyway, so it's going to go positive. So, but anyway, you end up with, what I get? 24.41. So that's how long, let's use a different color, that's how long this vector is. So these two components kind of build this fuchsia vector here. So the negative 1420 is the rectangular form, but the real arrow that's going on is that fuchsia one. And that's why I like polar form, is it kind of gives you a truer idea of what the vector really is. It's got a length of 24.41. Now we should solve for the direction. I think I'll solve for this angle right here because I know I can do some SOHCAHTOA real quick. So the tangent of that angle, I do this, 20 over, I'll just say over 14. I'm just analyzing that triangle, right? And so that tells me that theta is, what I get? I got a 55.01 degrees. That's what I got for that angle, 55.01 degrees. Now to write our answer, we're going to say that the magnitude, the length of the arrow, is 24.41, and the direction is, okay, be careful. Don't just grab this because you have to think about it a little bit first. You have to say, well, wait a minute, I want standard position, exclamation point, and standard position comes from the positive x-axis. It goes like this. So if this is 55, this is 180 minus 55. It comes out to 124.99 degrees. There we go. Okay, cool. Oh, let's see. Oh, now we got two examples. We're going to go the other way, from polar to rectangular. So, Bart's vector has a magnitude of 800 and a bearing of north 30 east. So they're telling us how far and which way. That's good. Draw this thing. Well, which way is north 30 east? Oops. North 30 east. You face the north, you turn 30 towards the east. That's over here someplace. So I've just turned 30 towards the east. Okay, and this thing has a length of 800 because that's what the magnitude of 800 means. So I'm try to draw that like this. Okay, cool. That's our vector. It's a nice polar form. I like that. So we drew the vector. Now we want rectangular form. Rectangular form is going to be like, okay, think about where that point is. We're going to go so far along the x direction and so far along the y direction to get there. So this is SOHCAHTOA. Anyway, if I'm looking at this triangle, that's a right triangle. If that's a 30, that would be a 60. So I could do things like, well, I'll call that y, I'll call that x. I could do things like, well, you know, the sine of 60 there is going to be y over 800. And by the way, the cosine of 60 is going to be x over 800. I did say 800, right? Yep. So if you solve this out real quick, you'll get y equals, turn the page, you get y equals just about 692.8. Right, a little less than 800, we'd expect that. And if you solve this one out, you get x equals like 400. And so, here's your answer. Along the x direction, 400. Along the y direction, 692.8. Cool. Let's try another one of those. Come on, you. Magnitude of 120, bearing of south 70 west. Okay. So that means we're going to face the south this time. Face the south. We're going to rotate or turn 70 degrees, which is a big turn, towards the west. So we're turning sort of like this. That's turning 70 degrees towards the west. And there we are. And this has a magnitude of 120. I'll just label that there. I drew the vector. That's done. Express it in rectangular form. That means get to this point. How far along the x-axis? How far along the y direction? Well, again, if that's 70, I figure that's a 20 then. Call that a y, call that an x, and then I can do my SOHCAHTOA stuff. So let's see, that would be the sine of 20 degrees equals y over 120. And if you solve that out, you get y equals, what I get? I got a 41.04. Okay, cool. And then if you do cosine instead, adjacent over hypotenuse this way, that's x over 120. And so x is equal to, I got 112.76. Okay, cool. So what is my rectangular form? Well, along the x direction, I've got this. Do I? Well, wait a second now. Isn't that kind of going in the negative x direction? I shouldn't put the negative there, but it's going in the negative x direction. So I should say that the length of this line really is 112.76. The trig doesn't lie about lengths and stuff, but it's in the negative x direction. Come to think of it, so is that, right? Our y is down here. It's in the negative y direction. It's a left and down kind of a vector, so put a negative here as well. So the moral of this story is, and maybe I'll put this in like a few shush. Always consider whether these are positive or negative directions. If something's in the negative direction, you got to put the negative there. Okay. So you got to be a little careful when you're going into the rectangular form like that. Okay, so we've had some practice going into polar. I want to scroll back up, take a quick look at that. Yep, going into polar, you mostly had to worry about what? Putting your angle in standard position. That seems to be what we had to worry about. Here, what you had to worry about is whether x component was really positive or negative and whether the y component was really positive or negative. Well, now that you've paid your dues, I might as well show you these shortcut formulas. These are nice. So if you have, call this the Vx, call this the Vy, because that's polar, excuse me, that would be rectangular form. They want polar form. That means they want r theta. Well, we got formulas for r and theta. Dun, 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 dun. Now, why didn't I just give you these formulas in the first place? Because even though they're nice formulas, you still got to be careful. be careful with these. And now you know what's at stake. You have to check whether your x's and y's are really positive or negative. You have to make sure your angles are in standard position. These are the kinds of things you got to worry about. So use the formulas, but then worry just a little bit before you circle the answer and go home. So first I'll start using the formula. Just plug right in. So the formula says r equals the square root of vx squared plus vy squared. So that would be the square root of, the x component is a negative 30 squared. The y component is a negative 40 squared. And if you plug that in, you should get a 50. Now make sure your calculator gives you a 50 and not an If it gives you then I know what the problem is. If your calculator is giving you an then the problem is, note. If you type it in this way, and I've seen this happen a million times, you type in the negative 30 and then you hit the x squared button, you know what you're going to get? You're going to get negative 900. And that's not what you want. Notice it's only squaring the 30. It's not squaring the negative 30. And so that's why it gives you a negative 900. So you got to be very careful about how you use your calculators. So you got to make sure that you use parentheses. Then you can hit the x squared button. And then you'll get the positive 900. Or if you're like me, it's Pythagorean theorem. I know I'm going to square it. I don't even bother to type the negative. It saves me from typing the parentheses. So you could just type 30 squared plus 40 squared, and it's the right answer, right? But here's the thing to be careful about. Just make sure you never do this. Just don't do that, okay? Anyway, that's the r. So be careful with your r a little bit. Now let's do the theta. So the formula, I'm just grabbing this formula right there. It says do a shift tangent of the Vy over the Vx. So the first thing to be careful about is sometimes people get this upside down. Don't just pick any old order. It's got to be the y on top and the x on the bottom. So in this example, the y component is this one. Negative 40 goes on top. The x component is this one. Negative 30 goes on the bottom. And by the way, I'm going to have to kind of move this stuff, get it out of my way. Maybe I can shrink it a little. That'd be nice. There we go. That's cool. Okay, so by the way, notice I am typing in the negatives here. And when you do that, you'll get an answer of, I haven't turned the page yet, 53.13 degrees. Now, can that be right? Well, look back over here. Our vector is negative and negative. Negative in the x, that means go left. Negative in the y, that means go down. We're supposed to go left and down. Where's 53 degrees? That's in the first quadrant. That's right and up. That's no good. That's no good. Now, you might remember what's going on here if you can remember back to Biff's two-answer theorem. Recall Biff's two-answer theorem for tangents. Sometimes when you hit a shift tangent, the calculator gives you the right answer, and sometimes when you hit the shift tangent, it gives you exactly the wrong direction. You have to add 180 to get, what would that be, 233.13 degrees. Is that right? Yeah, 233. That's the right direction because this is left and down, and that's what we want, left and down. Okay, so our correct answer to this one then is 50 at an angle of 233.13 degrees. That's the correct answer. So you might want to highlight maybe even a fancy color. We had to add 180, right? Now, how did we know that we had to add 180? Because the original vector is left and down, and all we're doing is changing the form of the vector. We're not changing the direction of the vector, right? We're just changing the form. So if it's left and down, it's still supposed to be left and down. You can't say, well, you can't make it right and up all of a sudden. No, it's left and down. We must have to add 180 degrees. That, by the way, is why we have these two asterisks, a double asterisk, because it's so important to keep that in mind. When you hit the shift tangent button, make sure you're checking whether Biff's two-answer theorem is in play here. You might have to add 180 to your answer to get it right. All right, one more example. Now, for this to be true, rectangular form. We would kind of want this to, go like that, but that's the closest I could do on my keyboard. Anyway, here's polar form. We have a magnitude of 140 and a direction of 210. Where is that? It's always a good idea to draw it. Where is that? 140 at a direction of 210. That's over here someplace. Okay, cool. That's the 210, right? Standard position. Let's just grab the formulas, though. They want rectangular form, which means they want Vx and they want Vy. Come up, look at the formulas. I love these formulas. R cosine theta, R sine theta. There were asterisks on them, so we'll have to be careful in a second. But R cosine theta, R sine theta. So if I just plug in the stuff, that's the R, that's the theta. So this says 140 cosine of 210. This says 140 sine of 210. Okay, cool. And if you do that, you end up with, well, 140 cosine 210 ends up being negative 121.24. And 140 sine 210 ends up being actually just negative 70. Whoops, equals a negative 70. And so you would write x component negative 121.24. Y component negative 70. And I can circle that with confidence. What could go wrong with these formulas? Well, the only thing that you have to worry about really is just be careful that when you're plugging these thetas in, if you want to use these formulas as is, you have to use standard position. You have to measure your angle from the positive x-axis. And this one did. So because this was standard position, that meant that we could trust these answers. Don't just plug any old angle in. Like if somebody went like this and drew a vector and said, oh, that's a 40-degree angle. You can't be plugging 40 into these formulas. That's not going to work. You'd have to plug in the standard position, which would actually be, I don't know, maybe 230 or something. That's the angle you'd want to use, not the 40, the 230. So don't get too fast, or whatever the word is. Don't get too careless. The formula, you can't just use a formula with any old theta, because you'll get different answers for different thetas. So which theta do you use? You use standard position again. Okay, so that's why these formulas have asterisks on them. They only work as is if you use standard position. Of course, we saw back a couple pages that you can just like look at it and say, oh, that should be negative, or oh, that should be whatever. You can also just use your reality check by making a sketch and saying, well, that can't be right, or that can be right. So that's kind of minor. Make sure it's in standard position. This one over here with the this double asterisk one, go away. This idea that sometimes you have to add 180, that's a crucial one. Make sure you're careful about that. Well, I think that ends that one.